ADIA and your host for this session, which will explore how multimodal AI systems are visualizing medical imaging and diagnosis with us here and diagnostics. With us here today, we have two speakers who are making an impact and shaping the way we approach diagnosis today and in the future. Our first speaker is Dr. Huazhu Fu, Principal Scientist at the Institute of High Performance Computing, A*, Singapore. His research focuses on medical image analysis, AI for healthcare, and trustworthy AI, with over 200 publications in leading conferences and prestigious journals. He's also been named among the top 2% scientists worldwide by Stanford. Shaping with us his insights on trustworthy medical AI, addressing reliability and explainability in vision language models for healthcare. Please join me in welcoming Dr. Huazhu.
Okay, thank you for the introduction. And my name is Huazhu Fu from the A*, Singapore. Here is my title of my presentation. It's about how to enhance the reliability and explainability for vision language model for healthcare. Okay, we know that recently AI achieved remarkable progress, so it has a potential to be a game changer for the healthcare. We can see that a lot of clinical workflow will changed by AI, and we also found a lot of great model, for example, the foundation model, GPT model, generative model have proposed and change our healthcare. Let's see some remarkable works. First one is Red Font. Is published in 2023 in Nature. It's first used the foundation model to train the model on the eye disease, and it showed that the foundation model can improve the downstream task significantly. And they also saw that the foundation model can also be used in community-based screening. The second work is PLEEP, is proposed by Stanford, and he saw that we can use the international public information to train a CLEEP model and combine the tag and image together to train the model, can improve the several downstream tasks, for example, the zero-shot transfer learning and retrieval. Yeah, in this year, actually, in last month, there are another paper is called IFM is proposed, and they used the large-scale ocular image to train the foundation model. And one interesting point is that he tested the model on the RCT. He saw that the foundation model, the large language model, or the large vision language model can get very better performance on the real clinical setting. But we found that we have a lot of foundation model or generative model or vision language model, but can we use it in the real setting? Here we saw that the GPT is very popular recently, and is on the medical question and answer task. At the beginning, the Microsoft or Stanford proposed the board-based GPT, the large language model. They didn't perform well, but after the GPT 3.5, proposed by OpenAI, the performance achieved 60%. And recently, the Google achieved a higher performance, even the 90 or above the 90% for the GPT, for the medical Q&A task. But there are some paper or studies, not that actually the GPT is not good enough for the real medical setting. For example, there are poorly performance on the medical coder, and has a limitation, is not easily integrated into the existing clinical workflow. So we think that even we achieve a very good performance in development, but can we deploy the foundation model in the real clinical setting? Let's say this finger. When we develop the AI model beyond the accuracy, we collect the data from different hospitals, and when we train the model, we focus on the performance or generalizability, and we hope our model can be adapted in different clients. But when we deploy the model in the real or in the open clinical environment, we need to focus on the more, for example, the trustworthy, the safety or privacy or reliability for this. So we can see that it's a gap between the development and the deployment. So our work is focused on two topics. One is reliability, one is explainability. So in this presentation, I will show some works about these two topics. The first one is reliability. As I mentioned about that, there are a lot of works achieve very high performance. For example, for the X-ray detection, is achieve 95% accuracy. But all these models have no awards of its confidence. So it's very dangerous, or it's a main risk for the clinical. For example, when we deploy the AI system in the real setting, it will be an open environment. They will face some low quality data or abnormal case. So if the model still give the prediction with this low quality data, definitely the results are not reliable. So that will be a risk. Let's see why it's happened. Actually, when we train the model, we found that we have an assumption that the test data should be similar with the training data. So it's we call it the in-distribution assumption. So when we deploy the AI model in the for this test data, they output the single prediction. But when we deploy the AI model in the real world, we will face some rare disease, low quality disease, even the abnormal case. We call it out of distribution data. For this out of distribution data, the AI model will still give the prediction, the signal prediction. Definitely, it's not reliable. So how to solve this? For our big proposal solution is called uncertainty. Actually, we change the single prediction to a set of predictions so that we can calculate the means and the variance of this set of prediction. We use means as the prediction. We use the variance as the uncertainty. Uncertainty is a kind of evaluation of the confidence, so that if we get a very low confidence, we can trust the results. And if the high uncertainty, we will refer the data to the expert to human double check. So from the finger, we can see that most model, even the best model, sometimes they will be overconfident because they cannot identify the abnormal case. So it's quite high risk. So the uncertainty estimation can help us understand what the model faced. So the uncertainty will tell us when we can trust the model prediction. Here's our recently study. We built an AI system, more reliable AI system to solve this issue. For example, here the standard model is training on the closed set because we need to collect the training data. All these data are limited category and limited appearance of the data. So when we face the data following the distribution, the standard model will give the prediction. But for some out of distribution data, for example, the rare disease, they will give the error prediction. Our model, we introduce the uncertainty, as I mentioned above, that we transfer the single prediction to a set of prediction. So we calculate the distribution variance as the uncertainty. When we have uncertainty, we can get the confidence level of the model. So the low uncertainty, we trust the model. For the high uncertainty, we can we can consider is the out of distribution date. For example, some rare disease or abnormal disease. So this is the whole system. Okay. We test our model. In several different data sets. One is internal data sets and two external data sets. We compare our method with the standard AI model. We found that because we utilize the uncertainty for training for optimization model, so we get a higher performance than the standard AI model. Besides the results, we can, because our model outputs the uncertainty, so we can use the thresholding to filter the unreliable results. So we only keep the reliable results. So we found that all the reliable results, the performance very high, even the about 90% for accuracy for the unseen data set. We also, based on the uncertainty, to test for the rare disease. Here are some data sets for the rare disease and some low quality data sets and abnormal case. We found that our method can identify these cases. Here are visualization. The middle one is the standard AI model. They just give the prediction, but for our model, for the rare disease or low quality image, we give a very high uncertainty to alarm the input is not reliable. So based on uncertainty estimation, we can get a more reliable result. We also extend the uncertainty estimation to the foundation model. So we load a pre-trained model and use the LoRa to efficiently fine-tune the model and add the uncertainty estimation. Interesting, the performance is quite good. For example, we achieved 95 or 94 on data site. Also a very challenging public set, we still achieved 77%. After remove the unreliable results, we get a very high 94 or 95 accuracy on all these data sites. In this study, we also test our model compare with the human. We ask several 30 experts from different level. For example, the expert more than 10 years experience, and the senior doctor and junior doctor to ask them label some rare disease or challenge disease. We compare with them, and our model achieve very high performance. One interesting thing is we also test the same site in GPT-4, and we see that the GPT performs very low. So that is so one potential reason is that the GPT-4 they have a lot of knowledge, but all this knowledge are general knowledge. They are not designed for the specific task, because our data set is for specific rare disease. So with the specific knowledge, without this specific knowledge, the GPT-4 performs lower. Beside the foundation model, we also think about how to use the uncertainty estimation in the vision language model. We found that we can use it to solve the hallucination. We know that the hallucination is the biggest challenge for the large language model or vision language model. Here are two definitions of the hallucination in different models. For the large language model, the hallucination means inconsistent the real world fact or user input. But for vision language model, it's a misalignment between the vision and the text generation. For vision language model, for the hallucination in vision language model actually is, I think is quite challenging and danger and high risk for deploy our system in the real world. For example, when we ask the question for the GPT or for the vision language model, the hallucination will give the error results. Here are some hallucination detection methods for large language model or vision language model. First one is we can train a detector for hallucination. when we get the answer from the VLM, we use the detector to identify whether it's the hallucination or non-hallucination. The second way is cross-checking. Actually, is something like a mixture of the expert. We can ask several different models to output the results, output their results, and then find the consistent results as the final result. The third one is external fact retrieval. We will use the retrieval to double check the answer. The third one is visual evidence verification. We can use each answer to rebuild or reconstruct an image and compare this to image, whether it's consistency. But all this method has the limited. For example, here for detector, we need to collect hallucination data to train the detector. For the cross-checking, we need additional model, and is high computational cost. For the retrieval, is need external knowledge based. For here is because we depend on additional expert vision model. So all this has a limitation. So we found that we can choose another way is uncertainty estimation. It means that we can give the confidence evaluation for the output for each sentence. And when we get a high uncertainty, it means this sentence or this answer are not reliable. It's a high probability to be a hallucination. Here is a very famous paper. Is published in Nature last year. They propose a semantic entropy for large language model. Actually, is when we input a question, they can generate different answer to change the similar questions. And then they calculate the similar semantic means and choose the high probability one as the final results. So we actually, for vision language model, we can transfer this way for vision language model. For example, we can add some translation or transformer in the vision, and we can estimate the vision results, the vision uncertainty. But there are two challenges. One, if we use the strong vision perturbations, and the image will change. So the results, the clinical diagnosis feature will change. So it will give the error. But if we use the weak transformation, the model will overlook the noise. So it cannot give the reliable confidence. So we propose our method. We combine these two types of transformation together, and we use the vision transformation. This transformation will not change the image, the diagnosis information, so it can calculate the results, diagnosis results based on the image. The second one, we introduced the trusted semantic distribution. So for this is distort the image. So it means that we will change the diagnosis information, make the model output a different answer. So we compare the original answer and the distorted image answer. We can find that which result will change. If the result change, it means that these results are more reliable with the image information. So compare these two, we get the probability of each phrase, so to detect the hallucination. We compare our method with different baseline. We get the higher performance in the on two data sets. Okay, besides the reliability, we will give another topic about explainability. Actually, we can imagine when we go to the hospital, the clinician will give some diagnosis, analysis, or based on your image. They will explain why is the abnormal or why is the disease. They also indicate the where the region is not health or not normal. But for the vision language model, we found that all the vision language model, they will give the answer directly. This answer is for the global image. They didn't identify which part is abnormal. So we can see that the vision language model, actually they can thinking, but without seeing. They don't have the visual understanding because the model is work as a black box. He gives the conclusion, but without explanation. So this is the gap between the diagnosis and the visual elements. The second one is visual hallucination. As I mentioned above, that for VLM hallucination, the key is the misalignment between the image and answer. So for this, without the visual content, we cannot identify each phrase of the model output. Based on this, we propose the medical vision grounding. It means that when we give an image and one report, we can identify each phrase from the report, and we can also identify the region corresponding to each phrase. So by this way, we can get a more phrase level alignment between the visual image and the results. To achieve this, we propose our method is called UMed Ground. Actually, we based on the multimodal large language model. We input the image and input the report. We can get the bounding box first, and then we combine the image feature with the box decoder to identify which region is. So for our method, for our framework, we get 3 outputs. One is the phrase. Identify the phrase from the report, and then identify each corresponding box from the image, and then give the uncertainty for each box to identify whether it's reliable enough. We test our method on 2 data sets, comparisons with other models. For example, we compare with the GPT, and we also GPT-4o because it can input the image and output the results. We found that the GPT-4o, the pure GPT-4o, the performance is quite low, only 7 or 10 performance. This is for DICE performance. And we also test the Lava with fine-tune and vision language model fine-tune. The performance still low. Our method get the best performance, combine the phrase detection and grounding. Here are 2 clinical applications. One is when we give the image, and we can embedding our system into the medical vision question system. So for each question, we can give the prediction, the region prediction for each answer. So we can get more visual funding from the VQA system. The second one is grounded class localization. It means that when we give an image, when we give the label, and we can use the GPT or large language model to generate a report and compare them together to identify where the abnormal region. Actually, for the second, for this application, we can use it on the weekly supervised learning. For example, you can consider in hospital, there have a lot of medical report, and they have the image, but they have no phrase level annotation. By use the grounding, we can identify the phrase region from the image. The third one is we can also output the report grounding for our original purpose. Okay, besides that, the technical, we also build our data set is GMAX data set. As the traditional medical VQA data set, they only have the closed and open-ended tabs, but without the phrase level box. For our data sets, actually, we extend the two types of VQA. We introduce the single choice and multi-choice. For each choice or each reasoning, we give the bounding box annotation. Oh, here is the how to construct the data set. Actually, we're based on the public data set. We ask the clinician to double check the bounding box in the data set and use the large language model to compare the bounding box with each phrase. And then we also, based on the grounding, we also use another GPT or large language model to generate more high quality vision question answer pair to enhance our model, to enhance our data set. Based on this data set, we do a benchmark, compare the different kind of vision language model, and the results are from two sides. One is the grounding, whether it can identify the bounding box. The other is the answer, whether it's involved based on the visual grounding, whether the answer will improve. We found that both two metrics we get the higher performance compared with the SOTA vision language model. For the grounding, we found that most of SOTA vision language model actually they didn't perform so well on the grounding. For example, even the GPT-4o, they achieve a very low performance. For example, 28 vision score or 23 vision score. But for our method, even we use a very simple fine-tuning, the Lava might achieve a higher performance based on our constructed data set. And for the answer, we get the better performance because beside the answer directly, we can identify the visual region. So it's can consider as a visual reasoning, so get a more reliable result. We also extend the visual grounding combined with the thinking, the deep thinking, because we think that for language model, there has the chain of the thought, but for image, it can be built a visual chain of thought. So we use the grounding as the visual reasoning. It means that when we give the reasoning for language, for each reason, we can give the corresponding bounding box. So that so based on this way, we can get a visual chain of thought. We also build we extend our previous GMAX grounding data set and combine the chain of the thought. Actually, it's based on the large language model. We input the report and the grounded report into the large language model. It will separate the each grounding to corresponding phrase and build the whole data set. Okay, we test whether the visual chain of thought can make the model better. We compare with the pure or original grounding data set and compare with the visual grounding. And we use the self fine-tuning, supervised fine-tuning, and reinforcement learning fine-tuning. We can that for the actually for the open-ended the original is better, but we get a comparable result. But for the close end, the visual COT get a better performance. Here are some visual results about visual COT. The first one is the grounding, the middle one is without the visual COT. The last one is the with the visual COT. We can say that for the pure grounding, it only give the result, the bounding box, but it's cannot corresponding the answer with the image. So the answer, the reasoning will not depend on the image. But for our model, we said we can see that all the reasoning have the corresponding box. So it's answer, it's a reason, and with a corresponding box. So it's combine the visual information into the vision language model, can get a more accurate output. Okay, so here's some conclusion. We call back our first framework. Our work focuses on how to deploy the model into the real world. So we focus on the reliability or explainability. For the reliability, we use the uncertainty estimation because it can evaluate the confidence level of the model output. For the explainability, we introduced the medical vision grounding, so we think it can be bridge the visual feature and test the answer. Based on these two techniques, we can move to the next stage in the future, for example, the AI clinician collaboration. Because we focus on the healthcare, actually, we think how to combine our model into the real clinical workflow and make the clinician trust our system. So if we can give the answer, for example, if we use the uncertainty estimation, for the low uncertainty, we can trust the AI model directly, but with a high uncertainty, we can ask the human in the loop to refine the results. And the visual grounding actually is a good way to open the vision language model, make the clinician know what's the thinking of the model and where the model look at. So it's a good way to enhance the trustworthiness of the AI model. Okay, that's my talk, and all this paper and the data set can download from my homepage. Thanks.
Thank you, Dr. Fu, for the great presentation. We have time for one or two questions.